going to present you a paper that we recently wrote about ontology projecting onto a manifold. It's entitled Towards Symbolic and Numerical Artificial Embedding. So it is quite clear then that this topic is raising a lot of interest right now, given this workshop. And our focus on our team is mainly on how to model human cognition. So with regard to psychologically plausible spiking neural networks, for example, but also drawing from psychological frameworks and psychologically inspired symbolic reasoning. So our approach might be a bit different from what was discussed earlier, since we are more working with social sciences and biology in the biological fields. So what we propose to kind of combine these approaches, biological and psychological approaches, is to provide a geometric mapping of ontologies onto neuronal manifolds. So what I mean by that is that we will try to focus on ontology frameworks such as RDFS, the Resource Description Framework Schema, or OWL, the Web Ontology Language, and find a projection. Oh, sorry about this. Can you still hear me properly?
Yes, I can hear you.
Okay. So onto neuronal manifolds, which are a way of representing symbols possessed by spiking neural networks, for example. And in this frame, we will focus on frameworks such as the web vector symbolic architecture, the semantic pointer architecture, which is a subset of the vector symbolic architecture. And the SPA is itself part of the NEF, which is the neural engineering framework that we will also discuss. So just to set up the context, so the vector symbolic architecture is a way to encode symbols as vectors. So it's kind of a localist view. Vectors will be sampled from the unit hypersphere and drawn from a high dimensional vector space, so that random vectors will be approximately orthogonal. And this is a biologically inspired view, which is compatible with what we know about spiking neural networks activity represented as neural manifolds. So why do we need the vectors to be approximately orthogonal? This is because we are using a dot product as a similarity measure to compare the semantic meaning of two vectors. So the interpretation of this dot product value can be in closed-world reasoning assumptions, for example, that 0 will be obtained when two vectors are very semantically different, and 1 will be when two vectors have the exact same meaning. We can also find more nuanced approaches, such as in an open world reasoning assumption, we would have a tau which can be either equal to -1 or -0. And in that case, 0 would correspond to an unknown value and -1 to a false value. And finally, we are also have in mind to extend it to more model values, so drawing from the possibility theory, where tau would be comprised between -1 and 1, but in a continuous one-dimension axis. So I will not develop this point any further. For now, we will focus on discrete values for tau. So now, just to structure the universal discourse a little bit more, so symbols will correspond to resources, as in the RDF vocabulary, with we distinguish classes, so concepts, individuals, instances of concepts, and properties, so roles. And we will structure knowledge into triples, as in the RDF formalism. But we also introduce the possibility to weight those triple with the tau value that we introduced earlier. So each of these resources, the subject, the predicate, and the object, will all be represented as vectors, while the Tor value is still a scalar. So how do we store and how do we represent these triples in the neural network? So those vectors, the SP and O, we need to store this relationship between them. And for that, we were thinking of using an associative memory in which the key would be the subject of the triple and the value would be the object and the predicate bound together. I will explain then what I mean by bound, and maybe scaled by the Tor value. So this is what we would obtain with only one triple, but if we add more triples, we would have more key value pairs. And finally, if we have, for example, more predicate object pairs associated to the same subject, in this case, subject 2 would be bound to, would be associated to several predicate object pairs, then I would superpose this pair in the value field of the associative memory. Oh, I'm sorry, I need to.
1 minute more, please.
Yeah. I'm really sorry. I will be leaving because there is a lot of people in this space because I'm attending another workshop session. Very sorry about that. Okay. So. So finally, what we need to introduce in order to have these representation is scalar multiplication to be able to scale the bound vector, vector superposition to be able to superpose two predicate object pairs, and vector binding, so which I will develop right now. This is all part of the semantic pointer architecture proposed by Elias Smith. And this binding that we are using is the vector divide transformation binding, which has which offers a non-commutativity, which is useful for us because we don't want to be confused between the predicate and the object. So what is also convenient is that the neural engineering framework, which encloses the SPA, also provides associative memory, as we described, implemented in spiking neural networks. So this is also available. Okay, yeah, I will just drop the Tor from now on and give a very simple example of how we can use that. So this is a very simple ontology describing Luigi eating a pizza. A pizza would be an instance of the concept margherita pizza, and the margherita pizza would itself be a sub-concept of the concept pizza. And what we want to infer is that the instance this pizza is also an instance of the concept pizza by transitivity of, by inheritance of the properties of the pizza concept. So this is the relationship that we want to infer. So we can see that with the formalism that we described earlier, we need to bind together type and subclass, this type and subclass predicate, and we need to make a single binding, so type binding from that. So we need actually to simplify a double binding into a single binding. So to do that, we will store an inference rule into a second associative memory. In that case, I will store that the double binding type and subclass can be simplified as a single binding type. So this is, oh yes, so I'm just finishing on the architecture of the network that we would use to solve this inference. So first I'm starting with a Q, this pizza, which is the subject of interest, and I'm retrieving the object predicate pair associative memory margherita type. And then I have a second Q, which is the predicate of interest, that I am unbinding to the predicate object pair margherita type. And I can then retrieve just the object margherita, that I will also lookup in the associative memory to retrieve the predicate object pair pizza subclass of. And I will bind the two together and obtain this final binding. And now I will apply my inference rule. So this inference rule will allow me to retrieve the inferred object pizza, which I can then bind to the inferred predicate, which is the result of the rule associative memory, and get the inferred statement, which is that this pizza is of type pizza. So we can also plot the activity of the neurons on these circled numbers that I'm showing. And so the activity of the neurons allow us, by comparing the semantic similarities of the vectors with our vocabulary, to retrieve that in the output, in the final output, we can get the inferred statement that we wanted, that this pizza is of type pizza.
Thanks,
So,
Chloe.
yes.
Sorry. Oh, yeah.
Thank you very much
last slide.
for your attention.